one lecture to go, a double lecture to go, and then the research talk. And I think you're 100% right. The research talks do come at a different pace typically than the teaching lectures. So that will be evident for sure. So at the end of the last session, we were still, I challenged you to go work through a couple of tutorial questions. So I wanted to start just maybe flipping through what really happens with those drugs. On paper, you can write a lot of things out, but in reality, sometimes only some of them happen. So maybe we can click through a couple of those examples here. Linazolid was the first one that we looked at, and several structures are present in the drug. The predominant metabolism occurs on this morpholine ring system here, so you can get O dealkylation. If you get O dealkylation, you can get to metabolites like this that simultaneously occurs with N dealkylation, which would be the process right there. So the initial O dealkylation would make something that looks like this, and then the N dealkylation would cleave this carbon-nitrogen bond, and that is a process that occurs to a reasonable extent. Additionally, you see a lactone, or this type of a substructure here. You have an alcohol and an ester, and that can make an alcohol and a carboxylic acid that can make an ester. Not something we predicted, but chemically it makes sense when you just think about basic reactivities of those functional groups. The other key metabolite derives from N-dealkylation. You get a substructure looking like this, and that undergoes clearance. So hopefully the types of things that you would draw in this case, the fluorine atom does modulate the metabolism a little bit here. Maybe a key point to note, a second reason why we don't see as much metabolism here, is that in general, drug metabolism typically occurs on the periphery of molecules. It usually doesn't happen to the middle of the molecule. You know, think about a molecule approaching that heme, and that heme is kind of in a cavity that's kind of like a cone. It's conical. And so the appendage of your molecule needs to be able to stick into that cave, basically. And so many times it's difficult for the middle part of a molecule to fit down into towards the heme and the P450. So more commonly, you're looking at the periphery of the molecule as the sites of predominant metabolism. Now the second one, dasatinib, is a kinase inhibitor, BCR-ABL kinase inhibitor for leukemia. And this has all kinds of substructures all over it. And you could predict a lot of things, and in reality, a lot of things do happen. So there's all kinds of stuff occurring to this molecule. Maybe we just start over here. We get benzylic hydroxylation. Hopefully some people saw that. The electron-rich aniline can also undergo aromatic oxidation. Okay, now this specific metabolite has two resonance donating groups in addition to an inductive donating group. So it actually undergoes further redox chemistry. It can further oxidize, and that's when you get to this quinone, iminoquinone type substructure. And so this can actually be hepatotoxic. It can be bad for the liver because this can react with other proteins. Now, when we look at the rest of the molecule, there is not that much metabolism going on through the core of the molecule, as I mentioned before, and it's usually the peripheries, the appendages, the things that can stick down into towards the heme. Those are the sites of predominant metabolism. So you see some oxidation of the alcohol by T03 A. That's just abstraction of the CH bond. It makes an aldehyde, and then you do it a second time and it makes a carboxylic acid. N-dealkylation can occur. You get a metabolite like this. You can also get some N-oxidation. There's a nucleophilic lone pair of electrons. Certain P450s will do that transformation too. Not one of the main ones we covered, but it still happens. Okay. So hopefully these are some of the metabolites you might have drawn on your own for homework. Maybe we can look at sertraline. This is a neurotherapeutic, and the structure is shown there. This has a couple of metabolic processes that occur. The amine itself can undergo dealkylation at two different positions. There are two different alkyl groups coming off of that amine. The demethylation process can occur, and you get to this primary amine. But you could also, if you look over here, that's an aliphatic system over there. So you can get N-dealkylation the other way, also in this case, and that's a benzylic position. That benzylic position is always also activated. So if you do N-dealkylation over here on this side, you get to the ketone, the decalone system. Okay, so that's how we're getting there. You can also, again, do the first dealkylation, then do the second dealkylation, get to the same metabolite. And this has been rigorously established. You can see which P450s are responsible. Sometimes it's like one or two, sometimes like everything does it, and this is the case where everything does it. Phase 2 can also happen, and we predominantly talked about alcohols and the examples we looked at, but amines are also nucleophilic and can undergo phase 2 processes or conjugative processes. And so here's a series of glucuronide transferases that'll transfer they'll transfer glucuronic acid over to your substrate. In this case, it's going to be tethered to through a carbamate. Okay. So, how are we doing? Some people draw out those, I hope. Okay. Okay. We already talked about this example, the final example that I had there. I actually forgot to present and give you guys a question, but I think you have most of the slides for this. You can see where the sites of metabolism are, the big greasy T-butyl system. There's a lot of grease over on this portion of the molecule. You can also get some O dealkylation here. And that can actually undergo further redox chemistry, but I'm not talking about that right now, okay? So again, hopefully people would look at this type of molecule and predict those two metabolites. This ring is electron rich. If you see aromatic hydroxylation, maybe you would expect that to occur over here. This one is more deficient. Those nitrogen atoms pull electron density away from the pi system. And so you would anticipate, just based on electronic structure, that this one would be more deactivated relative to this one. Okay. For aromatic hydroxylation purposes, also, for aromatic hydroxylation purposes, we might look at this ring. The T-butyl group is slightly donating, but the sulfonamide, this is a strong electron withdrawing group, that SO2. And so you are electronically deactivating this ring system over here. Now there's no fluorine on this drug, and that's fine. There are derivatives for which you can use fluorinated substituents to decrease the metabolism. So here's some representative T-butyl replacements that one might explore. And so again, that's in the slide. So I'm going to pause, see if there are any questions about those examples. Are we good moving forward and jumping into the next formal lecture? Let's do it. Okay. So let me close that slide deck. We are now on November 7th. Is that right? All right, November 7th. So it's tricky because back in the US, they're going to sleep. So I had to call home this morning and say, God, what day, what time is it over there? When I'm saying good night to family. But here we go. This is a fun one, ligand-protein interactions. This is a fun lecture. It's very physical in nature, and hopefully everybody learned something from this one. And you have to write it down on your reports too on the PDF. You know, talk about how much you learned. You can use this slide deck as a source. So, drug design, drug discovery, zeroth law. I've covered this a couple of times. In order for a drug to exert pharmacological action, it needs to get to the site, it needs to persist in the site, it needs to circulate throughout the body for a sufficient amount of time that it exerts pharmacological action prior to clearance. Okay. So we covered a lot about that circulation, the distribution, the clearance, but now we have to ask the question, well, what if that drug actually does get to the site, the intended site? And what if it does engage the receptor? How might fluorine perturb the interactions at that receptor? So now we start asking that question, and we start thinking about intermolecular interactions. And so I've summarized those here. This is a 2-slide summary. We're going to walk through the different types of interactions that are common for fluorinated substructures. These are kind of summary figures, but we'll talk through these in more depth as we go through. And then in a second part of the talk, probably after the tea break, we're still taking a tea break? Yes. Okay. At what time officially? 11:15 or okay. Okay. In a second series of examples, we're going to talk about how fluorination can change the acidity and basicity and really perturb other binding interactions. We talked about basic amines. We're going to talk about some other ones also, and how you can have unique functional groups for which fluorine really drives the reactivity of that group. Okay. So let's just first start with the multipolar interactions. This is a classical interaction now. It was recognized just over 20 years ago by Francois Diederik. And so this is an electrostatic interaction. It's an interaction for which the CF bond's dipole presents the anionic portion towards an electrophilic carbonyl. So it's electrostatic in nature. It's not a hydrogen bonding interaction. It's roughly perpendicular to the carbonyl. You can see representative examples of the CF bonds. These are models that come out of the crystallographic database, the structural database. And we're just looking at the pink ones. The green ones are something else. The pink ones are your multipolar interactions. And all of these interactions, the fluorine is pointing mostly towards the carbonyl carbon. And there's a certain distance and certain angle associated with this type of interaction. So that's what this chart is for. It's looking at the angle of the interaction. 90 degrees, that's perpendicular. Here's our carbonyl, here's our CF bond. It's like that. The chart, you can see the curvature here. You can see the curvature, okay? The chart indicates that when you're close to 90, when you're close in distance between the fluorine and the carbonyl carbon, that thing is perpendicular. Within 10 degrees, that thing is like that. As the distance increases, the angle can change a bit. Okay? And that's what you're seeing out in this region over here. As you get out past 3 angstroms, towards 3.5 and maybe 4 angstroms, you see more variability in the angle, but the CF is generally presented towards that carbonyl carbon. And again, it's electrostatic in nature. The rough distances associated with this interaction are here if you're looking at crystal structures or computational modeling using whatever computational package you prefer. That's what you're looking for. The CF presented towards the carbonyl at roughly these distances and roughly this angle. The energy associated with this interaction is about 0.5 kcal per mole. A little more, a little less. There's a little bit of error there. But it's a reasonably weak interaction, but it can be pretty profound in drug discovery campaigns. So in a follow-up manuscript publication, a series of matched pairs were analyzed, and in this case you'll have like H versus F, CF3 versus methyl, CF2 versus CH2. So that's what we're looking at in matched pairs. These types of substructures, and we're going to compare the affinity of the drug for the target as a function of H versus F. And in this analysis, you get an increase in potency at the target 50% of the time. Okay? If you can observe this interaction in your crystal structure or your docking model, you have a 50% chance of having a more potent compound when you put fluorine in there. So it's a coin toss, 50-50. Okay? Sometimes you have no change, sometimes you get a decrease. So why not try? About a 50% chance of a lot of things in life, that's actually a pretty good chance, right? So the suggestion here is, or it's an explanation of, yeah, sometimes you put it in there and it's making a nice interaction. Sometimes it's not really doing much. Sometimes it gets a little worse. Why not try? But recognize it does get worse sometimes. It can be no change sometimes. If you look into this data set here, the distances where you get an improvement in potency are typically outside of 3 angstroms. Okay? There aren't many examples for which the fluorine to carbonyl distance is less than 3 angstroms. So if you start getting too close, it's not likely going to be in this bin where you get an increase in potency. Okay? So it's something to think about. I know we kind of, on the previous slide in the previous study, gave you a range here. That was from this 2003 paper. This one's a little bit newer, a different analysis, and it's suggesting you should actually be looking outside of 3 angstroms, not that 2.8 in that range. Just don't worry about that, is what this one's suggesting. Okay. Do what you want in your own programs, but that's just a suggestion. Now remember fluorination. If you fluorinate molecules, we already saw in several other lectures that you can improve other properties. So if you get no change in potency, but you've improved other properties, that can still benefit your program. Similarly, maybe there is a slight decrease in potency, but other molecular properties, other metabolic properties, other distribution properties improve. That might still be the right way to go for your personal campaign, for your drug discovery campaign. So don't take this out of context. Don't say this is always bad. Sometimes you get benefits in other properties even if your potency goes down. So keep that in mind as you move throughout your career. So the discovery of this interaction, again, I mentioned it's over 20 years old now. It came from an analysis of a series of ligands for which fluorination was systematically studied around a benzylic ring coming off of the substructure shown here. The pocket had several residues. It was a well-defined pocket, and it provided an opportunity to say, what's going on if I fluorinate each position? And in this specific case, there was one position, the 4-fluoro position, for which the potency increased pretty drastically, and the selectivity versus other enzymes also increased. So look at that change in potency relative to other examples in the class. We're going to come back to this later on, like pretty late in the lecture, and look at what goes wrong when you have bad binding interactions. But right now we're just asking the question of what's going to be good. And the analysis that was conducted with a specific enzyme identified the multipolar interaction that I was just mentioning. So the fluoro at the 4 position is presented towards the carbonyl carbons. Okay, that's this one right here, 3.5 angstroms, and the rest of the environment was also analyzed. And when you do that analysis, you can then go back into the crystallographic database and see how many other types of co-crystal structures have this type of substructure. And it turns out that quite a few do. The multipolar interaction that I was indicating is here, but there also seemed to be quite a few structures for which there was some type of favorable interaction with the C-alpha. Dr. Deepak on day 1 was talking about the acidification of the CH and how there's many interactions between a CF bond and a CH bond. And it turns out that many times this multipolar interaction, since it's close in distance, this carbonyl is close in distance to the vicinal CH bond, by default, you also see an interaction there, okay? So that's what's going on here. This is what's called a fluorophilic environment. It's been analyzed by many individuals. You're really looking at the carbonyl fluorine interaction, but also an interaction sometimes with the alpha CH. And that makes sense, right? If we're pulling the carbonyl, if we're pulling the CF bond towards the carbonyl, and the next carbon over is going to be pretty close also. And I think that's what's going on in this case. So there's some more data for you to walk through and look at. I provided on the slide. The paper is fantastic, like it's really rigorous science. It's a great one to dig through, and it's a fluorine classic. One key note is that when you look at these plots, there are gaps. So there are some areas that you should stay away from. You can see a gap down here below 2.4 angstroms for D2. You can see a gap over here. Now this axis here is D1 versus D3. So it's D1 versus the carbon distance right next to it. And so basically what it's suggesting is that if you have a short distance for D1, you can't be far on D3, right? If this distance is close, that one can't be far away. Kind of makes sense when you just think about geometry, right? The second one is also interesting. If we look over at this chart, below 2.4 on D2 doesn't really happen. So you cannot get this distance too close. Okay? So that's a second point to think about and just consider, and there's a lot of data points, but those I think are the two main messages. And it's not a bad chart to look at if you ever try to use this type of strategy or analyzing a crystal structure. You can always open up the paper if you know these charts are here and go back and look at the data in real time as opposed to trying to memorize these things. These are things I wouldn't memorize normally. Okay? So there are some regions that you want to avoid if you're trying to rationally utilize this strategy to drive potency. Okay. So these interactions, I said, had been found in a wide variety of crystal structures. So we pulled a couple of them from my group. This is probably from 2017, 2016 when we were building up the initial slide decks. And so I'll just show you a couple that we pulled out of the literature. Here's an example where you have a couple of interactions, 3.5 angstroms over to one carbonyl, but you also have another one. The next position over also presents a carbonyl at just under 4 angstroms there. You can see an increase in potency from these types of interactions when you assess the data for the match pair. Okay. Similarly, another example. This is another match pair for which we get an improvement in potency, 6-fold improvement by placement of a fluorine atom here, 3.2 angstroms for the fluorine atom to either of the carbonyls. Another evaluation, another estimate, you can see it right there. Now in this case, the alpha carbon there has a distance where you think, okay, maybe that secondary interaction is also present. In this one over here, you can see the alanine methyl is actually presented towards. So this CH bond is going to be presented off the page. So that one does not have the CH bond associated with the interaction. Okay, so the CH bond is kind of optional. Sometimes it's there, sometimes it's not. But in many cases, enough cases, statistically it is present and it can be favorable. Okay. So those are the multipolar interactions. They're also really important for at least one really important approved therapeutic. This is the development of Lipitor. This is the #1 selling drug of all time for well over a decade. It was making $11 billion a year for Pfizer, for about a decade, some maybe about 15 years ago. So in the initial discovery, this was the pharmacophore. So this is a pharmacophore. It actually saponifies. You get an open chain substructure, and that replicates a metabolite, HMG-CoA, that the body uses to make other steroids. So initially they were studying this series. You can see a heterocycle. When you go back and look at the older literature, they had a variety of different heterocycles that they were exploring. In many cases, they were doing SAR, evaluating SAR on an arrow ring here at the 2 position relative to the aliphatic system here. So the fluorine atom at this position drove affinity pretty significantly, potency pretty significantly relative to H. And other polar substituents, hydrogen bonding substituent here with the hydroxyl also improved affinity. You can see methoxy was a little bit worse, chloro was okay. And that study, after further analysis, decades later, right, this is 1990 and this is 2001, they realized what's really going on here, and you have a multipolar interaction. I introduced that multipolar interaction initially for a carbonyl. But other C something double bonds, in this case a CN double bond, also has electrophilic character, delta plus character at that position. And you can see the distance, 2.9 angstroms. You can see the improved potency of the ligands and match pairs at this position. So ultimately we have another multipolar interaction that was present for well over a decade, but nobody really realized what was really going on with these systems. Okay? So that's what's going on there. It's one fun story. You can see how the rest of the drug ultimately developed, a little bit more grease over here, coming out of this position when you get to the methyl group. And then you can further build greasy substituents off of these positions over here. And yeah. Cool? Okay. Yeah.
You have written there no interaction with NH with and CF. But it is probably the polar interaction will be with carbonyl basis.
Yeah. Yeah. So that's what a multipolar interaction is, and nature chose to do this. Nature chose to say that there's delta plus character there, and there's an electrostatic interaction. Now, intermolecular hydrogen bonding interactions is like the very next section. I'm looking at the next slide. And so that's like the next section. And we're going to talk about what else can happen. But also recognize that the geometries to have some type of an interaction with the NHs there would be different. You'd have to have some type of a rotation of the side chain of the amino acid to be able to get proper alignment. So we can cover that in like 2 slides.
also you have means previously you have told means there is intramolecular hydrogen bonding probability is more than inter in case of fluorinated compound. So,
Absolutely. Intermolecular hydrogen bonding is controversial. Some people say it doesn't exist. But there's a different explanation. And like we're one slide away from it. So may I move forward and then let's get to the end of the next section and then we can pause and come back and come back to this question or discussion. So that summarizes the multipolar interactions, at least for an initial introduction. There's so many examples out there in the literature. There is other literature that follows up on the papers I've presented here. We can now move and talk about the polar interactions. So when we talk about polar interactions, these are the interactions that some people think are hydrogen bonds. Okay, now hydrogen bonding interactions require the lone pair of electrons kind of reaching out to a proton, and there's some type of an overlap, but fluorine holds its electrons really close. In many cases, the interactions, when you look at the crystal structures and the distances, like they're not within distance for those lone pairs to actually be reaching out and grabbing the proton. So there's another interaction that can also explain that same feature, and it's dipoles. You think about magnets, plus charge, minus charge, plus charge, minus charge. You might have a good alignment of the dipoles that's still favorable. It's not the overlap of the lone pair of electrons reaching out to a proton, but alignment of the dipoles can still be felt through space and at longer distances. And that's the other explanation in this controversial argument about intermolecular hydrogen bonds. Okay? So I can walk through that a little bit more. Sorry, I left my tool over there. So we can talk about that a little bit more on this slide. Okay? Hydrogen, or these what we'll call polar interactions, are typically weak. Less than a couple of kcal per mole. You get a good hydrogen bond, like 5 kcal, 10 kcal per mole. You get higher, but you easily get 5 or 10 kcal per mole. These are like minor, less than 2, sometimes less than 1. In terms of the dipoles that I was just talking about, think about the electronegativity of a CF bond, right? Anionic at fluorine and a acidified proton that would typically engage in a hydrogen bonding interaction. That's going to be delta plus, and this is going to be a heteroatom, delta minus, and it's going to be an electrostatic interaction, alignment of those dipoles that's driving the affinity. Okay? So that's the alternate explanation. I've seen heads nod. We're kind of okay enough with the background on this type of an interaction. They are a little bit weaker than a good hydrogen bond. They can be used to tune molecules pretty well, late stage selectivity. You can get some affinity, but it's not always that great. So here's an example. This is Januvia. This was one of the examples when we were looking at oral bioavailability, and I said, you guys go calculate the pKa. Somebody did it. We walked through the math, and it was like a 5-fold difference in pKa between these heterocycles over here. So we've seen the drug structure, and now we can start thinking about not the pK properties, but we're going to start looking at the affinity properties and what happens when you walk through systematically substituents on the ring and on this position here. How does that affect potency against the anticipated target? In general, these are very selective ligands. These are other anti-targets that they're trying to avoid, and you don't have much interaction with any of those. So I'm not going to discuss the right hand, but that was just included to show we have good selectivity for the scaffold. So in the initial subset of molecules presented here, you can see the R2 group is increasing in terms of grease, steric bulk. You're going to see an increase in potency as you just put greasy substituents into that space. The CF3 is definitely more potent. But you don't necessarily have a huge jump. That's like 3-fold, 3.5-fold. That's not amazing for getting 3 fluorine atoms well positioned with good intermolecular interactions. Those are pretty minor improvements in potency there. In contrast, arrangement of the fluorine atoms, the monofluorine atoms around this ring seems to drive affinity much more significantly. And so in this series, we go from a 3,4 difluoro to a 2,5 difluoro. 4 is para, 3 is meta. So you're kind of going from this to a 2,5. Okay, there's a lot of examples in this MedChem paper. I've just selected a couple. And you see an increase in potency. That's a big jump. That's a 5-fold increase by just repositioning the fluorine atoms around the ring. It's just isomers of each other. So if you get your fluorine atoms properly aligned there, you can really drive affinity. You put a fluorine back in the 4 position, you drive potency a little bit more. This is one reason why many in the pharmaceutical industry, like, don't try to outthink nature. It might be easier just to build the subset of derivatives where you just like make as many perturbations as you can and just test them all and see what works and then come back and rationalize it as you're building your model and getting data to revise your model. Okay. Maybe if we're thinking too much, maybe we might miss one that would be good. And so you don't want to, so, you know, many times people will just try to make as many derivatives as possible when they're trying to tinker around with fluorine. So, anyway, we have our CF3 still here. If we take this 2,4,5-trifluoro and revert back over there, you see that we do retain some affinity, like we're still 2-digit nanomolar here. Remember, this substitution also drives the oral bioavailability pretty significantly. So you do want that CF3 there for other purposes. Okay. Finally, further tuning of the ligand says if you get too big, too bulky in that space, again, you lose potency again. So tuning, you know, how big and bulky the substituent is was pretty significant, and there was high selectivity there. You know, subsequently, the models demonstrated that in this case, you're dealing with the polar interactions, and the CFs seem to make interactions that aligned with the polar amino acids. These are ones that did not align with multipolar interactions. They seem to have better alignment with the fluorine kind of engaging the hydrogens in those substructures. You can't always predict it, right? The enzyme has some amino acids that are a little bit floppy. Sometimes it's a little bit more rigid of a receptor. And sometimes you might be predicting one, but the receptor reorganizes, and then you end up with an NH with an arginine instead of that multipolar interaction with an arginine. So, you know, sometimes you get one, sometimes you get the other. Okay, and there seemed to be some type of an interaction over here in this pocket with polar residues similarly. Okay, so these types of interactions do exist, and in other follow-up drug campaigns for the same target, individuals try to retain some of these interactions. So you can see other scaffolds that other companies have used to probe and or develop clinical candidates in this chemical space. This fluorine atom is retained even if you change a lot of the rest of the scaffold. Okay, so those are cool scaffolds, though, the way they've kind of jumped and really different chemical structures there. But that interaction is still really important. Okay, so the couple of interactions that we have talked about already are unique to fluorine, and many individuals will mistakenly call it a halogen bond or halogen bonding interaction. And that is absolutely 100% not true. It's chemically the opposite. And I'll explain why on this slide. So I'm trying to dispel a myth that any of these interactions, the first one we talked about, the multipolar or the polar-polar dipole alignment, those are not halogen bonds. So halogen bonds are bonds in which there's a sigma hole, there's delta plus character over in this space that's part of the Ci sigma star. I'm going to have another representation. We'll keep building the slide in a little bit. And you have a pi system, or nucleophilic lone pair of electrons present its electrons into the sigma hole. And so the orbital overlap diagram for this type of interaction is shown here. Again, the sigma hole is predominantly composed of the CX sigma star. That sigma star is kind of in this space. There's delta plus character there. The sigma hole accepts electrons from pi systems and or lone pair of electrons. Okay? And so the orbital mixing diagram puts 2 electrons down, no electrons go up, and it's in that stabilizing interaction. These can be up to 20 kcal per mole. They can be pretty powerful and really well-designed systems. The energy levels or reactivities of the sigma holes, the sigma star, increase as a function of the size of the halogen. So Ci bonds have bigger sigma holes than CVR, bigger than CF, and then, sorry, CCl, and then CF does not have a sigma hole. The CF bond does not have a sigma hole. You cannot project nucleophilic lone pair of electrons into a fluorine atom. That's bad. That's going to be electrostatic repulsion there. Okay. And you can see representative examples of the sigma hole in these examples here. CF4, there's no sigma hole there. Cl, there's a little bit of cationic character. Bromine, iodine, you see more and more and more cationic character in this space that can accept electrons. This type of a charge transfer complex. They're also called charge transfer complexes. Okay. So that is a halogen bond. The only way fluorine can participate in a halogen bond is if it's actually this over here, donating its electrons into the sigma hole. But still, fluorine holds its electrons close to itself, high electronegativity. It doesn't like to send its electrons out into this space. So these aren't, fluorine here, it's not a predominant interaction. It's nowhere near as common as having maybe an oxygen or a nitrogen. Okay. Now, fluorine can participate in a related interaction in systems, and so these are related charge transfer complexes by which you can present electrons from either a pi system or nucleophilic lone pair of electrons. You can present those into a sigma hole on a carbon-sulfur bond. So the orbital mixing diagram would look very similar. You have a sigma star from the CS bond. When it overlaps and you get this interaction with either the pi system or the lone pair of electrons, the electrons donate into the new mixed molecular orbital, this bonding orbital, but the anti-bonding orbital is vacant. So you get a net stabilization, and these can be reasonably powerful interactions. And you can see that the sigma holes that have been calculated, those sigma holes are anti to the carbon-sulfur bonds. This is a thiophene, but there's also sulfur in some proteins, many proteins. We have our methionines, we have our cysteines. So if you have, for example, a methionine, the active site or the site you're trying to ligate with a small molecule or a large molecule, the site you're trying to target, you might be able to engage the sigma hole with some type of nucleophilic residue in your drug. And yes, fluorine can participate as a donor in these types of interactions amongst other atoms, but fluorine can do it too. And this is a fluorine class. We're going to talk about the examples of how fluorine can work here. So in this series of molecules, you have a carbazole, you have the ethyl chain attached to it. The initial monofluorinated derivative presents into this is supposed to be going 3.4 angstroms to the CH there, 3.4 angstroms over here. And what we have is some type of an interaction that would look something like this. This is supposed to be going down into this space. We have an interaction that looks something like this. You have those multipolar interactions. It's just well aligned. You have conformational freedom in this ethyl chain for that fluorine atom and the ethyl chain to kind of find the happy spot over there. The CF2 unit still makes the same interactions over here, but it also starts to make an interaction over to the sulfur, and the CF3 actually reinforces that interaction. So in the CF3 version, you still retain the initial multipolar interactions we saw before, and now you see the really nice alignment here with the sigma hole, 180 degrees roughly, so it's presenting anti to the carbon-sulfur bond. The distance you can see there, 3.2 angstroms, looks like a bonding interaction. And you can see the improvement of potency from 138 micromolar, which it's not bad. This is a fragment-sized molecule. It's not a real drug yet. They need to build quite a bit more. It's a nice model system for understanding what's going on with the fluorinated substituents, but we can get down to a sub 40 micromolar compound with these substitutions. So Okay. So we can engage proteins through these interactions, through fluorine-sulfur interactions, but you do need to be aware of the distances and angles there and try to optimize those if you're going to have a success with these types of substructures. Okay. So those were several different examples of polar interactions that can occur. Let's talk about hydrophobic interactions. So what's the nature of a hydrophobic interaction? Maybe that's the first thing we should talk about. Generally, we think about drug design and interactions between a ligand and a target. We're trying to think of affinity interactions, hydrogen bonds, pi-pi interactions, side-phase pi interactions, multipolar interactions, just sort of favorable interactions. And those can certainly drive affinity by changing delta H. If we have an energy associated with binding, delta G equals delta H minus T delta S. We've known that since high school chemistry, right? Okay. So the molecular interactions that we've been talking about before really affect the enthalpy term, but you can also drive affinity by modulating the entropy term. And when we talk about hydrophobic interactions in a general sense, one way that these enthalpic interactions occur is actually by displacement of water. So you might have organized water networks within a hydrophobic cavity, hydrogen bonding with each other, water in that space. If and when the ligand displaces the water, that water is pushed out of the active site into bulk solvent, that is entropically favorable. That'll affect the delta S term, and that can also drive affinity. The greasy molecule doesn't like being in an aqueous environment, so it wants to push itself into a hydrophobic cavity. And when it does that, the displacement of water drives the delta S term. Okay? So when you have finely tuned, well-tuned grease of the right shape, right size, you can really drive potency. Now, when you add grease, you have to be aware that that grease could get metabolized, and then we've got to be concerned about other PK properties. So there's a balance, and that's why I was telling you about the lip-E, lip-met-E, those types of metrics. Those metrics evaluate, number one, when you put grease on the molecule, are you really gaining affinity? That was one of the types of metrics we were looking at. And in the other metric, we were saying, okay, if we add grease, how much is metabolism increasing? And you have to balance those. It's not like you can win all the time in both of them. Like you might make a change and one might go up, the other might go down, and you're going to be fine-tuning and balancing these types of properties. Nonetheless, the key point here is that we can also modulate affinity for a target through pushing water out of the active site. Now, this comes with several caveats, and so the generalization is not always true in specific examples. So in specific examples, you might have really well-organized water networks, and if you push a greasy moiety through a really nicely aligned water network, that might actually be bad for enthalpic purposes. So the general trend is shown here. Well-positioned grease can displace water and improve the entropy of the system, but sometimes that's not always favored in every single example. And many times the modeling systems most modeling systems don't explicitly track water that's bound right around the ligand there. Sometimes you have to actively model that in, and when you have like more extensive networks, that's even tougher. But there are some really nice examples out there of these hydrophobic interactions and what these hydrophobic pockets might look like. So here's one example. This is that cannabinoid compound, one of the ones we studied when we were looking at the PK. Remember, we started with a neutral phenolic ether here, and then we added electron withdrawing groups. Metabolism switched over here, and then they had to solve metabolism over there. That was that example. So in this system, the CF3 group actually improved potency. The data is back in your previous slides, but you also, it drives potency because you're presenting this moiety into a greasy pocket and pushing water out of that space. Okay, that's what's going on in this system. There are other systems that we're going to look at that allow you to really think a little bit more critically about the data and what's going on with water and reorganization of water. So this is a match pair analysis of a cyclic nucleoside. So you can see that the nuclear base on both sides, and then you can see the cyclic nature right there. Okay. Crystal structures for these can be obtained from the crystallographic database. In the crystallographic database, the compound with a hydroxyl group has a nice hydrogen bonding interaction with water. 2.4 angstroms, the fluorinated ligand, so the fluorine right there is this R group right there, the fluorinated derivative, longer distance, probably a little bit too long for a real hydrogen bond, so it does not have a really tight association with the water. Okay. Now, let's look at the data for these two compounds and see how that demonstrates the difference in enthalpies in binding for these two compounds and also the entropies of binding for these two compounds. So, the fluorinated compound is a more potent ligand. And this was established multiple different ways. You have a thermal shift assay that's melting the protein, and if you have a melting point for protein, and you then put a ligand in that protein that stabilizes the protein, you should see an increase in the melting temperature of the protein. Okay, so when you have a larger change in melting point, that means your compound is binding more tightly to the protein. Okay, this general feature can be used for lots of different assays, but this is what's called a thermal shift assay, and the fluorinated compound binds more tightly. So the dissociation constant was also measured, and you can see it's a more potent compound by almost an order of magnitude. Subsequent, now both of these, all this data suggests that the fluorinated compound is more potent. It's a better binding energy than the non-fluorinated compound. So there's a study, ITC, isothermal calorimetry. It's pretty common in drug discovery and or enzymology that can measure the delta H and T delta S terms and differentiate those, give you quantitative numbers for those. That assay demonstrated that the delta H term for the hydroxyl containing compound was much better. You can see that almost 5 kcal per mole better. But the enthalpic term was better for the fluorine. And the change in enthalpy was sufficient to make the fluorinated compound a more potent compound. Okay? So the data is telling you that it's the entropy that's a lot better here, even though the enthalpy is better here on the hydroxyl. So there was a couple of other examples in this paper. I think this second example over here is a pretty powerful one in my mind. The difference is that in this side you see the symmetry in the two heterocycles there. Okay, both G's. That's this exact same example right here. You have G, G. If instead you have an A and a G, it's a different compound. But the overall trend is still the same. The fluorinated compound is more potent when you have the dissociation constant measured. The thermal shift is significantly different, and you can see delta G is definitely better for the fluorinated compound. When you break that down into the entropic and enthalpic terms, when you break that down into the entropic and enthalpic terms, it's shocking to me. This is crazy. The delta H of binding is actually positive there. But the T delta S term drives the affinity and makes this actually a very, very, very potent ligand. That's crazy to me. Okay, so I think this is a cool example to study, read a bit more about, and see what the authors say about it. So I'd encourage any of the papers that I put up here, I'd encourage, to dig deeper if it interests you, but this is a pretty cool one. Very physical in its treatment. So I want to get through one Yeah, two sub-stories. This one will take a hint to develop. The second one's going to be quick, and then we'll break. So I'm shooting for 10 to 15 minutes for the tea break, and we'll be good. So you can ask questions about, well, if I have a methyl group, when should I put a CF3 there? If I have a CF3, when should I switch back to methyl? And there's a couple ways to go about the question. You can think about it a lot and try to convince yourself one way or the other. You can just make it. That's what I tell my group. Like, think about it, but also make it, because your thoughts might be wrong, okay? Try the experiment. Test your hypothesis. You're predicting that it'll be bad or better. Now you have to test it, right? So what we're going to do here is start asking the question, well, if I have maybe some crystallographic database or a binding model, and I have a methyl or a CF3 group, like, when should I put a little bit more effort into making the other derivative? What amino acids in the direct vicinity seem to favor one versus the other? And so this is a computational study here. Just to calibrate everybody with what we're going to see in just a minute, we're going to have red, blue, and green lines on a chart. It gets a little bit tricky when you have several lines on a chart. Those are just distances between the group and the amino acid that's in the vicinity. Red, blue, green. Okay. So you can see that the distances will be on the next slide. Now on the y-axis, you're going to see a ratio from the crystallographic database of, does the amino acid typically prefer CF3 or methyl? Like, if they just go in there and dig data out of the database, which one is common, which one is more preferred? Okay. And that's going to be a bar chart, and it's going to get pretty crazy. Now, this model evaluates and looks at electrostatic interactions and polar solvation energy. So polar solvation, that's like water, right? We're just talking about the entropic interactions, dehydration of a ligand, but electrostatic is also important there. Okay. So your slides are a little bit more complex right from the get-go, but I'm going to walk through it in a couple of quick steps here. So the first series of data is going to look at what happens under a distance of 3 angstroms there. And under 3 angstroms, you'll see a couple of amino acids that seem to have a very strong preference for a methyl group over the CF3 group. Okay, so you can, in this column right here, you're taking notes, you want to maybe jot down this. Under 3 angstroms, you have a methyl group, it's probably going to be your better choice. Okay, if you're leucine, your cysteine, your isoleucine. If you are under 3 angstroms and have phenylalanines, and maybe some other ones, but phenylalanine jumps out at you, man, I'm thinking about trying to get a CF3 into that space. Okay, statistically, that's favored. Not thinking about what interactions specifically ongoing, we're just looking at the statistics on what the crystallographic database says here. Now, as we get further away, that distance increases, 3 to 4 angstroms, a couple of other things jump out. Maybe in this region you had no preference, but now we have asparagine preferring the methyl, CH3 more common. You have a flip in selectivity, so if you get a little too far, phenylalanine no longer prefers CF3, now it's kind of preferring the other way, a little bit, slightly. Okay. So you get different trends as you move away. And so over here, these spots are just for you to look at that chart, make an analysis, and maybe jot down some notes yourself in your own free time. But note that there are some preferences that are distance specific. This is our, gosh, I'm trying to see, is that lysine? So this down here, so this is methionine, right? So our methionines, sorry, the angle I'm at, I'm having trouble seeing the difference between methionine and lysine on the chart. So our methionines prefer CF3 if you get just a little bit further away.
Cysteine does not, like, cysteine also has sulfur.
Yeah, it also has a SH versus a neutral sulfur. So there's a different acidification, there's a different environment there around cysteine relative to a methionine. Good.
Yeah, something related question, because in these 20 amino acids, so when in the amino acid there could be CONH or the residue, or it could be anything. Is it like
This does not predict what the actual interaction is. This analysis doesn't consider that at all. It doesn't tell you what physical interaction is present between the ligand and the target. It only tells you that there's a trend, that the CF3 tends to be closer to that type of amino acid in the database.
But I still have, like for example, lysine has the epsilon amine.
Mm-hmm.
So are we talking about the interaction of that amine with the CF3 or the, because then there is a
yeah, so I think those are more of the side chains that we're looking at.
Side chain.
Yeah, side chain preference. Okay. It's a model. There are lots of models. Ultimately, it takes a chemist, a person, a dedicated scientist to make the molecules and test them for your particular target. Okay? So that leads to this question. I thought you were going to this question. It's like, how do I know when I might have one interaction as opposed to the other? And ultimately, you're going to need like data and or crystal structures, docking model. Something's really going to have to help explain why you're getting changes in affinity. Okay, data is way better than modeling, but modeling is a great early estimate as you're going through a program, and they're great for predicting. But crystallographic data, cryo-EM, some measurement is always, in my mind, a little bit better than a model. Okay, models are very useful, nonetheless. So, in general, there's a nice series of papers from Anna Volpetti, who used to be at Novartis, maybe still is, I don't know. And they established a trend based off of NMR scores. So if you have more D-shielded shifts, you tend to have more of the hydrophobic or multipolar interactions. If you have more shielded fluorine atoms, as estimated by NMR, you tend to have more of the polar interactions, the one that look like H bonds, hydrogen bonds. So those are, it's a trend. It's a statistical analysis of the database. It does not always hold true for every example. Okay, this is just a trend, all right? There's nice papers. When you go into this one, you do see a lot of pictures of what they're looking at and the type of geometries they're seeing. I've talked about most of those types of interactions, so I don't think it makes much sense to go re-look at those interactions. This is just looking at statistics and data here, okay? So it's a nice series, it's a nice paper to, again, calibrate yourself with. And again, these are evaluated by distance from the target and some other metrics too that might help you use it more intelligently in a campaign. Look like you're about to ask a question.
Is it like multipolar interactions are like stronger than the hydrogen bond?
Yeah, so the multipolar interactions, those were typically about a half kcal per mole. They can be a little bit stronger. The polar interactions that kind of look like a hydrogen bond, again, the rough estimate is less than 2. That doesn't mean 2. It doesn't mean 1.5 or 1. It's just less than 2. It might be 0.3, 0.5, okay? So they vary, but they are still reasonably small. They're nowhere near as strong as your typical hydrogen bond that you would anticipate from a good hydroxyl group or appropriate NH or an amide linking onto something properly. Okay, so there's just a little bit more comments. I've commented on these things in the previous slide, but just a little bit more text that supplements what I said. I think this is mostly redundant with what I've said, but just for your own notes. So this is the point that I thought was going to be 11:10 to 11:15, but it's 11:08 and 45 seconds. Can we still break now? Is that okay? I think it's a good point for a transition before we get into the last few slides. Is that good? Okay. We come back at 11:25.
Yes, we can back.
Is that still good? 11:25. We can come back.
Yeah, but I still have one point regarding.
Oh yeah, one more question, comment.
I was predominant whenever they are observing. So I personally thought that when we are planning, as a chemist is planning to incorporate fluorine, so what I took a message on, and also some little bit from your like last 2 days of teaching. What I thought maybe depends on the if we are more into hydrophobic pocket, and you want to like have a check the fluorine presence, maybe then if it is hydrophobic pocket, then we should like have a different plan. If it is a if it is a hydrophilic pocket, then we should have a different plan. Like from your previous slide, you had that all interaction to follow. So maybe we can thoughtfully incorporate changes based on also the what kind of pocket like our residue is lying. So will that I think really help?
I think that's true for all medchem, that you should always be thinking about what's the nature of the amino acids and opportunities to develop your ligand or design your ligand. Like you should be thoughtful about the pocket and what's there, and then try to design things in that seem reasonable. Also think broadly, and one derivative doesn't always test your hypothesis well enough. You might need to make 2 or 3 derivatives. It also helps to have 2 or 3 hypotheses. And so, maybe it's more of a hydrogen bonding interaction that we can get. So we want to make a couple things that have more nitrogen, oxygen in that vector. Or maybe instead we can get more of a polar interaction. So we need fluorine, which is going to be stronger as a dipole, and that might be the better one. So, it's the same residue that we're trying to get to, but we can get through it through an electrostatic interaction or a hydrogen bond. Or maybe there's something just next to it that we might also be able to engage. So we should think, instead of just ortho, we can go over meta and try something else. So, I think having several hypotheses is always good.
Yeah.
Yeah.
So I think this is very important. Like when we are trying to do medchem and we have 2 to 3 hypotheses, and again for each hypothesis like 3 to 4 variables, so that we can actually test our hypothesis. So I think that is what I think should be a good idea.
Yeah. Okay. Good. We'll break for a bit. We'll be back in a little bit.